All right, now we've reached section 2.3, which covers bivariate data. Bivariate, by the way, to remind you, means data that's represented with two characteristics. So if you recall in chapter 1, we talked about the dimensionality of data, right? And so in particular, these are data that have two dimensions, right? Two variables that they represent. And we're going to talk about how those two variables might be connected and how to display that connection. So to connect this to chapter 1, remember that we had a schematic about how we think about variables interacting with each other. So we may have an explanatory variable, and we're trying to measure the impact on a response variable. And of course, there's confounding variables, trying to attack that in the sense that our experimental design may or may not account for these variables and how they change that interaction. But with bivariate data, one really helpful way of thinking about this relationship and displaying that is to take data that has this as your independent variable and the response variable as a dependent variable. So you have an input and an output. And if this is jogging any memories of what you may have done in algebra, you're on the right track. So bivariate data looks like pairs x comma y, where all the first values represent explanatory data values and the second values represent response data values. And we can represent these in what we call scatter plots. So super important, scatter plots, you can only create them from bivariate data. There are more advanced versions of scatter plots with higher dimensional data. But when we say scatter plot, we mean bivariate data. And so I have an example here to pull up. We have a very basic example of a scatter plot. This comes from New South Wales state government in Australia. So this is from a publication of theirs. And they actually use simulation data as well. So this is not, real data, but it's a simulation. So what are we looking at here? So we have our graph, which is the scatter plot. We have a lot of these points here that are represented as little diamonds. And our horizontal and our vertical axes are represented, and an explanation of what each one means. Okay, so to clarify, what we're looking at here is our explanatory variable is the time that a patient spends with the doctor, right? So time with doctor in the outpatient clinic consultations. So time measured in minutes is quantitative, right? And our response variable is satisfaction score on a survey. Which is it's measured on a scale of 0 to 5, which usually means that this would be ordinal level data, but also quantitative if we make that stretch. So typically, scatter plots only work with bivariate data with both components quantitative. And the resulting scatter plot is actually each data value represented as a point where, for instance, this one right here, let me circle that better. Looks like that might be 5 minutes and a score of 1. And then up here, we've got somebody who spent 20 minutes with the doctor, and they gave them a score of 5. And when you're looking at these scatter plots, sometimes very characteristic patterns emerge. For instance, here we can see that there's a pattern where patients that spend less time with the doctor tend to give lower scores. These. And patients that spend more time with the doctor tend to give higher scores. Okay? So what might account for that, and how do we represent these relationships? And this is really at the heart of correlation. So correlation, generally, refers to any relationship between variables. It's very important to note, specifically for this reason alone, that correlation does not necessarily mean that we have found a cause and effect relationship. Okay? Correlation is evident from the sample. It does not necessarily generalize to what is true for a population. Okay? So it could be, we could have arrived at this scatter plot by random chance alone, if that makes sense. Okay? And so this is an example of a scatter plot where we might be looking at something called linear correlation. There's different flavors of correlation. So the particular one that we're looking at here is linear correlation, where it appears that there's a straight line relationship between the variables. Okay, so one variable changes, the other one changes accordingly, proportionately to the change in the explanatory variable. And there's a very helpful way of representing that here, where we're looking at scatter plots more generally and thinking about exactly what kind of correlation are we looking at. So first of all, this is another scatter plot. It's a sample data simulated. We'll get to the line of best fit in a second, but in general, if we look at our points, our data values on a scatter plot, and they tend to cluster, then that's a good indication that we have some sort of correlation, okay? And we have a lot of different kinds of correlation, okay? So obviously the first kind that we're going to explore is linear correlation. And there's really two flavors that are important. There's positive and there's negative. What does positive linear correlation mean? It means that as variable, in this case, they call it variable B. As variable B increases, right, then so does variable A. The negative correlation means the opposite. So as variable B increases, variable A decreases. Okay, so the arrows here represent if they're going in the same direction, right? So larger, for instance, in this case, right? So we have, So we have a data value with low variable B, low variable A, and another data value with high variable B, high variable A, and that's the trend. Okay, that's the linear correlation trend, which means this is positive. Okay, and there's other ways of representing. So this is the direction of the correlation, right? The relationship. But there's also the strength. So how strong is that connection, right? And you can kind of see from the schematic here that we may be looking at strong correlation if those values are those data points are really closely clustered together, right? So strong, weak, where you can kind of see a linear pattern, but not really. Like you have to kind of make a stretch there, and then what we would just say is none, right? That's just no. There's no correlation there at all. And again, whether there's strong, weak, or no correlation does not necessarily mean that we have a cause and effect relationship. However, if there is no correlation at all, right? So if we're in this case, then that's usually strong evidence against the presence of correlation. Okay. So all of this is highly theoretical, and as we kind of go over in the textbook, there's other kinds of correlation. So remember, linear is like you have a scatter plot and you can draw a straight line through it and it looks like it fits the characteristic. Same thing was true here, right? You can kind of draw a line through the middle of that cluster and it's like, oh yeah, that fits it pretty well. But sometimes you have, oh, it's gone. Didn't know that was possible. I'll bring that back. Sometimes though, you have scatter plots where a line just doesn't fit well, right? And so you can have quadratic correlation, where the relationship is just slightly more complicated. And so you tend to see more of a scatter plot that looks like this, maybe. And so I'm very generally going through what that scatter plot might look like. So it might look like this, right? Or you may have an exponential model. So an exponential correlation, highly important in the health sciences, in particular epidemiology. And it kind of looks like quadratic as well, except it's just much faster. And an exponential model, that typically is coming from if you're taking sample data and your explanatory variable might be, it could be time, and your response variable could be cases, number of cases. And you're just looking at different countries, different states, right? And there's a whole host of other kinds of correlation, but for the most part, we're going to stick with linear correlation. That's the one that interests us the most. Because with linear correlation, if you want to model that relationship, we get into what's called the line of best fit. And I'm going to leave that for a second video. But the idea is when linear correlation is strongly present, and there's ways of numerically deciding what is strong, what is weak, and we'll talk about that in a second. When linear correlation is strongly present, we can model the relationship using a linear, let me call it this, a regression line. So, like I said, I'm going to leave that for another video. But I want to briefly talk about what we call linear correlation coefficient. So this is our first statistic that we're actually talking about in any detail. It is represented by the letter R, and there's an associated statistic called R squared. And the R squared value, we're going to get into that in later sections about why that's important. But for now, R, linear correlation coefficient, it ranges between -1 and 1. So zero's in the middle here. And roughly, what we're talking about here is if the linear correlation coefficient is close to 0, there's no correlation. But if it's closer to 1, we have very strong positive correlation, linear correlation, of course. So this is all just linear correlation. And if we're closer to -1, we have strong negative correlation. So it's helpful that if it's negative, right? So anything less than 0, but close to -1, or it's somewhere in that range. We're talking about negative correlation. So that trend where it looks like it's going downward. And we have positive correlation if the R value is positive. And somewhere in the middle here, we have basically what we call weak negative correlation and weak positive. And the typical range of values here, usually if, we'll talk about that dividing line. It depends on the sample size, okay? So it really does depend on the sample size. And so this is kind of where we partition here, roughly at 0.7 and negative 0.7. And then roughly between 0.3 and negative 0.3, where we would just say that, oh, there's no correlation really between negative 0.3 and 0.3. Again, it depends on the sample size, so don't think that this is a hard and fast rule, right? But in general, the larger the sample size, the more clear your correlation coefficient is going to be telling you a picture about the correlation. And so when you have, for instance, your R is somewhere in this range or in this range, ooh, that's a very terrible bracket, then we have a strong indication that we should go and create a regression model.